So before we begin, let me tell you that there were some typos in the lecture when we discussed the change of variables. So I have fixed them, and always, as I always tell you, that follow the lecture note which has been updated. Okay, so follow the lecture note which we sent you, like the latest one. And in case you find any other typo, please let me know so that I can correct it. Okay. So in this lecture we continue our discussion on line integrals, and if you remember that we had kind of discussed this fundamental theorem for line integrals. Okay, so we start by recalling that and then see some of its consequences. Okay, so what we have a vector field which is given by the gradient of function of 2 or 3 variables. Okay, and we want to consider its line integral, okay, over a smooth curve which is parameterized by a vector valued function rt. Okay, and the fundamental theorem for this line integral is basically telling us that whatever this is, it is going to only depend on the endpoints of the curve. Okay, this is precisely what it is. And if you just try to relate it with the fundamental theorem of calculus, you see that this is precisely the analog or the counterpart here, isn't it? So we saw that the proof is basically writing it down. I mean, just expand the formula for the the line integral and use the chain rule and along with the fundamental theorem of calculus, because when I do the chain rule, what I am going to get here, a function of a single variable and its derivative, and this is what we need to integrate from a to b, and just fundamental theorem of calculus gives you the expression which we just wanted. Okay, so the proof is not just it's not about the proof, but this result is very important. Okay, even though the proof is simple, but this result is like one of the key results, and we are going to discuss today some of the consequences. So there are going to be some new definitions, there are going to be some new results. Okay, namely this idea that instead of this, if I have a vector field, okay, what can we do, and can we say that this vector field is written in terms of gradient? Because if that happens, then I know you have this theorem. All right. Okay, so this is what we are going to kind of talk about today. Yeah, so as I told you, like if your vector field is written as the gradient of a function, then the line integral of this vector field is going to depend only on the endpoints of the curve. Okay, so even if I change my curve without changing its endpoints, nothing is going to happen, isn't it? So a vector field in general which is given by the gradient of f, okay, so is called a conservative vector field. Okay, so these are the terminology. So the conservative, this comes from physics, this terminology, and I will try to tell you that why. Oh, and the function f is called the potential function for the vector field. Okay, so these are the terms which we might use while discussing some problems. And as I just said, like if you have piecewise curves, okay, so let's take two piecewise smooth curves which have the same initial points, same initial and the terminal points. Then if my vector field is conservative, that means it is expressed as the gradient of a function, then what will happen, that these two integrals are going to be same by the fundamental theorem of calculus, because this side is going to be only in terms of the endpoints of the curve, similarly this side. Okay, so no matter along which curve I integrate, if the vector field is conservative, the answer is only going to depend on the endpoints. Okay, so this gives you a lot of flexibility in choosing curves, because I may give you a very complicated curve joining 2 points, but if you know that you need to integrate the gradient, then all you need to do is you can just consider anything. You can take a line segment, for example. Okay, and often you will see that we will refer to these piecewise smooth curves as paths. Okay, because this is it's a we are joining 2 points. Okay, so this is also the notion of paths. Okay, So sometimes we will refer to them as paths. Okay, so okay, let us consider this situation that when I have C1 and C2 having the same endpoints. Okay, so let us say one endpoint or the initial point is A and the terminal point is B. So I go from here to here along with C1, and then I go from here to here along with C2. So this curve, and if I am going this way, these are two curves, C1 and C2. But you see, I have written here minus C2 because I have given the orientation, you know, from B to A. Okay, so that is the minus of C2. Okay, now why am I doing this? Now, you know, once I have two smooth or piecewise smooth curves between these 2 points, I can consider this loop. You see, I can follow C1 all the way up to B1 and then minus C2 and come back to A. Okay, so such a situation also you know, can be rewritten down in terms of loops. Okay, so what basically we are doing, we can join two curves, C1 with minus C2, and get a loop. Okay, so this is like again a path which starts at A and finishes at A, and such a thing will be called a closed path or closed curve. Okay, and this gives us the notion of independence of path also. Okay, so we say that a line integral of a vector field is independent of path if this thing happens. Okay, so this is precisely the meaning of independence, because it doesn't depend on which path you are choosing. Okay, of course, I mean, these two paths are not arbitrary. They have been having the initial and terminal points fixed. All right, so this, and we saw that this is the case when your vector field is conservative. Okay, so conservative vector fields are example for this situation. All right, okay. Now, as I said, if I just join these two things, then I can actually write this thing down, because C2 integral over C2 of this vector field can be written as integral over minus C2. Okay, but if you remember, when we were integrating the vector fields, there is going to be a negative sign outside. So if I bring it on this side, then there is going to be an integral over C1, and there is going to be an integral with minus C2. Okay, so you can club them together, because we know that if I have two paths, I can join them. Okay, take the union, basically that is what we are doing. So this whole thing can be written down in terms of, so if I call this whole path at C, then this is precisely is going to tell you that integral along C of this vector field is 0. Okay, so that is what we are going to just say. Before that, let me formally put this definition. So closed curves, okay, closed curves or closed path. So a curve or path is called closed if it has the same initial and terminal point. Okay, so for example, you take a circle, you can take an ellipse, you know, you can just take a rectangle, you know, so there will be piecewise smooth curve, and so on. Okay, and then we have this result, whatever I just explained, that the line integral is independent of path if and only if the line integral of the vector field along every closed path is 0. Okay, and I mean, we kind of just saw the proof here. Okay, because if it is independent of path, you are going to get this, and then what you need to show that the integral of f along any closed curve is 0. So basically, you take a closed curve, you break it into two pieces, and you get the answer, and vice versa. Okay, so this is a situation, or this is a kind of reformulation of this definition that line integral of a vector field is independent of paths. Okay, because now you no longer need to consider two different paths. Okay, all you have to do is you take any closed path or closed curve starting at a point, and then it is going to finish at the same point, and look at the line integral on that. If it is 0, then you know that this is okay. So as I said, the examples are definitely the vector fields which are conservative vector fields. Okay, because conservative vector fields, they depend only on the endpoints, and if we consider the endpoints to be same, then the integral is going to give you 0. Okay, so they are the examples, And why this term is used, because we, as also told you in the previous lecture, that the integrals, they are they determine the work done by vector field. So basically, conservatives simply means that the work done around a closed path is 0. Okay, there is net gain is basically 0. So that is the meaning of conservative. Okay, so but once I have this, that if you have a conservative vector field, then its line integral over any closed path is going to be 0. So it's natural to ask that what happens other way around. If I have a vector field, a priori I do not know whether it is conservative, that means whether it is given by a gradient. Okay, but what I know is that if I integrate it on a closed path, then I am getting 0. So is it also true that the vector field will be conservative? So that will be very good to know, in the sense that an arbitrary vector field, and if I can express it in terms of the gradient, that is very helpful. Okay, so the answer is yes, but we have to consider slightly better domains. Okay, I will introduce a new notion, which is the connected. So you are in R2 or in R3. Okay, open sets already So what is the meaning of connected sets? Basically, you take any 2 points in this set, and you should be able to join these 2 points via a piecewise smooth curve. Okay, and this curve should completely lie inside your domain. Okay, so basically there is a path between any 2 points of this domain, that's all. Okay, so that means anything and everything is connected inside it. Okay, so that is the term connected. And once I have that, then I can have this statement that let's say that you have a continuous vector field defined on a connected domain. Okay, so connected domain D, this could be in R2, it could be in R3. Okay, so this you have to, because I am not specifying, because it does not really use as such the structure of R2 or R3. Okay, so if the line integral is independent of path, okay, this means the definition in terms of 2 curves, that the 2 curves with same initial and terminal points, the integral is same. Okay, or you can also say that integral over any closed path is 0. Then the conclusion is that this vector field is a conservative vector field. In other words, we can write this vector field in terms of the gradient of a function. Okay, so basically, from the fact that the integral is becoming 0, we need to somehow express this in terms of the gradient of f. That means we need to kind of find this function f. Okay, so at the moment I am not going to give you the proof, but what I will do is I will try to solve some problems where we try to tackle this kind of problem, that how to find the gradient function for a given vector field. Okay, as I said, if this cannot be done always, because otherwise we don't need the conservative vector field notion. So whenever we have this capital F in terms of gradient, okay, one of these theorems will ensure that yes, you can do that, and then I will try to kind of illustrate the method that how does one find this F. Okay, so that will give you a clue that how to prove this theorem if you want to. Okay, and if I have time at the end of this course, I might give you a proof. It's just going to take hardly 5 to 10 minutes. Okay, now some other results which are kind of which help us in understanding the vector fields, the conservative vector fields, and so on, that how to determine whether a given vector field is conservative or not. Because sometimes if I give you a vector field with which involves slightly complicated functions p and q, and then you have to integrate it to figure it out whether it is conservative or not. Basically you have to say that it is either as gradient of f or integral is 0, correct, on any closed path. Then that might be a little challenging. So there are some results which tell you that something are necessary conditions for a conservative vector field. So this is one of them. So you start with a conservative vector field. Okay, so this is P and Q are going to be functions from R2 to R, and we of course always assume that this P and Q have continuous partial derivatives on the domain. Then this will happen. Okay, so if I consider the partial derivative of this function with respect to y and consider partial derivative of q with respect to x, then these two are going to give me the same function on the domain. Okay, so this is a necessary condition for a vector field to be conservative. Okay, now you see, given P and Q, this is so easy, just you have to take the partial derivative. Okay, so immediately you can determine if this doesn't happen, vector field can just not be a conservative vector field. Okay, all right. So proof, let us see. So what we are saying, that this vector field is conservative, so there is a guarantee that it's written as gradient of a potential function. Okay, so you do that. Now I have this capital F given via this P and Q, and also it is given as gradient F. So these are two vectors. You compare the components. Okay, and what you get, that P has to be the del F by del X and Q has to be del F by del Y, isn't it? Now you see, we are looking at these two quantities, so you just consider the corresponding derivatives. You take the derivative of this with respect to y, and then derivative of this with respect to x. So what you get on this side, you get del 2f and then del x del y, and then similarly then del 2f del y del x. But you know, we had a result which said that if the partial derivatives are continuous, which is the situation over here, okay, then these two quantities are same, so you get that this thing happens. Okay, so these are simple but you know useful results. Okay, so but again, this is only one way. You know, this tells you that this is a necessary condition. Okay, like in the previous theorem also, the conservative vector field says that the integral is 0, so that was a one way result, and then then we got this theorem which said that if this integral is independent, then the vector field is conservative. So that was the converse. Similarly, you can pose the question that whether this condition is also sufficient to make sure that this vector field is conservative. Okay, precisely this. Okay, so we have the converse of the previous theorem, which is just we just stated, and which basically is going to tell you that the condition which we laid down on P and Q on a given vector field is actually also sufficient to ensure that this vector field is conservative. Okay, so this you know, sometimes when you go for the converse, you need some extra assumption. Okay, so we are going to have some of the definitions. Okay, and this is so you start with a curve or a path. We call it a simple path if it does not cross itself. Okay, so situation of this is not acceptable when you are working with simple paths. Okay, this brings us, you know, this brings in some technical difficulties. So we avoid the curves which cross each other, or you know, which follow, because you know it can happen that I start from here and then start coming back. You know, those kind of situations are because things are counted twice, and then the change of orientation also happens. So those things are not going to be considered. Okay, so we are going to rather consider simple situations when a curve is traversing in a you know direction, and this is the meaning that it doesn't cross each other. That means the value of the parameterization, this is the equation which parameterizes the curve, this is not same for any 2 points. Okay, keep it clear that these are the points between A and B, excluding them, correct, because I can have the same initial and terminal points. If that happens, then the curve we will call it as simple closed curve. Okay, so simple curve is this, and then closed curve, you know that this is a loop. Okay, but not like a figure 8. Okay, all right. And then one more definition we are going to use. See, these are all the definitions which basically are imposed on the domain, and they kind of ensure that the domain is connected in such a way that we can perform these line integrals without really going out of the domain. And also, because we are going to talk about the derivative, so derivative will be nice if we have this notion of connected, and then simply connected is slightly stronger in the sense that for example, this domain you look at, okay, so the domain is the part which is shaded, and this whole is not part of the domain. Okay, now you see that if I take any 2 points in this domain, I can join them by the paths. Okay, so this is a connected domain. Okay, but it's not going to be a simply connected domain. Okay, because the definition of simply connected domain is such that says that you take any simple closed curve in this domain, then so I mean, just imagine a curve here. Okay, just like this simple closed curve. Then whatever it is, whatever is inside this curve, okay, whatever region it encloses or bounds, that region should be part of the domain. Okay, this is what it is telling. Okay, so for example, here if I take this already goes out, so I should bring it. Okay, then that hole which was there is also included in this domain bounded by the curve. So that is not allowed because it encloses something which is not part of the domain. Okay, so situation like this, when things are made of 2 pieces or when there are holes, these are the situations which are not included in the simply connected domains. So simply connected domains are simply those where you take any simple closed curve or path inside, and then whatever region it encloses, it has to be completely inside the original domain you started with. Okay, so basically you avoid holes. Okay, yeah. So if I put this extra condition on the domain, then you have a converse, namely that you start with a vector field on a simply connected domain, then and of course you assume this is always there, the continuous first order partial derivatives of P and Q, and assume that this happens. Okay, this is precisely the conclusion from the previous theorem. Then you can say that the vector field is conservative. Okay, so the necessary condition becomes sufficient if you have an additional condition on the domain. And note that in our course we are always going to have these kind of domains where the domain is disk, or it's driven by an ellipse or triangle, rectangle, or something which is bounded between 2 curves and so on, isn't it? So everything we are dealing is going to fit in this theorem. All right, so now let us look at some example which tells you that how to prove this theorem. Okay, see, there are 2 ways. Either I give you the abstract proof in terms of P and Q, or I give you a proof which involves some particular function here. Okay, but this is not the proof. I am telling you that I am going to illustrate the proof of finding the function f so that the capital F, the vector field, is gradient of f. Okay, I am going to illustrate this method, or one method rather, that how does one do it by an example. But that is not a proof. Even if I give you 1000 examples doing this thing, that cannot become a proof. Okay, proof will require reasoning in the general setup. Okay, so examples can disprove a theorem, but they give you an idea that how should one prove the theorem, but not they cannot become the proof. Okay, all right, so let us see. Suppose I have a simple example of this vector field. The question is this vector field conservative? And if it is conservative, can we find the potential function small f? Okay, so there are 2 parts. So first, and you see the domain is not specified over here, but you see this is just a polynomial equation in x and y, so is this, and they are so nice. they are differentiable of any order and the derivatives are continuous and they make sense for any x and y. So the domain here is whole of R2. We don't have to really worry about it. Okay. So in order to show that this is conservative or not, you have got all those theorems. You apply the one which is easier, isn't it? So it's easy to just see that this is P, this is Q, and if I just recall the previous theorem which says that if this vector field is conservative, then this this condition has to hold. Okay, so and then we prove the converse also. So since the domain is simply connected, we can use this theorem that this condition ensures that the vector field is conservative. Okay, so we just do that. You write down P, write down Q, and compute the partial derivatives as as required in this theorem, and see whether they are coming out to be same. And this is happening. Please be careful, because many a times I am unable to check all the calculations, because I am always talking to myself, so if there are mistakes, you have to be careful and then report the typos or the mistakes to me so that I can correct them. Okay. Yeah, and then we conclude immediately that the vector field is conservative. Okay, so whenever you see this kind of question in your exam, if you just say that this happens, then you have to refer to the theorem which you are using here. Okay, I can say that this theorem which is written upstairs here, but you are not going to have that theorem written in your notes already. Okay, in your answer sheet. So when you conclude, you state that theorem, that what theorem you are using. Okay, under what conditions that theorem is applicable. All right. Okay. So we are guaranteed that this capital F is going to look like the gradient of small f, isn't it? So there's going to be a function f. Now our task is to find this f. Okay, so idea is very simple. All you have to do is you compare these two vector fields. So this side you are going to have components as fx and fy. Here you have p and q. So you get a relation of the derivatives of f in terms of some functions. Okay, and this is precisely is going to happen whenever you need to find the potential function. Okay, this is what is going to happen. You have to solve some this is like a differential equation, or you have to solve some integral equation. Okay, all right. So what we do is we integrate this out, because if I am given the derivative of f and if I integrate it out, I am going to get f. Okay, but we have to be careful that what is the meaning of integrating it. Okay, the derivative here is with respect to x. So what I am going to do is I am precisely going to use the fundamental theorem of calculus, treating this as a function of just x. Okay, so for each y I integrate it and I am going to get this thing. Okay, so when I integrate this both sides with respect to x, I am going to get this. Now here you see there is something unknown here, g. What is this? See, when you integrate, there is going to be a constant of integration, isn't it? But this constant is not really a constant for all the time, because it depends on y. Okay, it's a constant with respect to x, but it's not a constant when if y change, this may change. So you think of it as a function of y. Okay, so from this you have got a relation which, so basically you see that in order to find now this function f, all you need to is figure out this g. Okay, and we have got another equation to do that. Okay, so if I want to do something out of this and this, what I have to do, I have to just differentiate this. Okay, so that I can put it over here and then see. So just you precisely do that. So when I do that, I get this relation. Okay, and simplifying it, the relation becomes this. Okay, so whatever this g is, it is going to satisfy this equation. And now again, this is a situation of one variable, the derivative is some function. Again you apply the fundamental theorem, so the g is going to look like this. Okay, and of course this constant is going to come because of the integration. So the general form of the potential function is going to be this, where this constant is k. So if you want some additional condition, that will determine the constant. Okay, so for example, you say that f of 0 0 is 0, so then k will be 0. Okay, so some initial condition or some extra condition will tell you that what is this k. Okay, otherwise the general form is just this. Okay, so you know, there are these very small results, but physically they are, you know, very useful. You know, in physics this language is used a lot, and the notion of line integral, and you know, they help you to understand the vector fields. Okay, now the next what we will talk about is the Green's theorem, okay, which we had been chasing for a while. This is going to be precisely the analog of fundamental theorem of calculus for double integrals. Okay, but I will do it in the next class. All right, see you.